Okay. Okay, first, quick public service announcement, if you will. And actually, even though this is based on a conversation of a student who's not in this class, but I think it pretty much applies to all students that I encounter, whether they're in this class or not. So there's one thing in particular that I often, during my entire time here, I've often had students say to me, and because it drives me nuts, I never want to hear it from students again. And what is that thing? I don't or didn't want to bother you. Often followed by, oh, because I know you're busy, as an excuse for not seeking help when help is needed. Knock it off. Or even if you haven't said it to me, if that's what you're thinking, again, stop it. Yes, as a breed, all professors are busy, although you guys are pretty busy too. I often joke that I'm the, quote, least busy faculty member on campus, not because it's actually true, but because I often hear from my faculty colleagues how busy they are, even when I know that I'm busier. And but I hear them whine about it more. So, but a lot of the things that I have going on, like any faculty member does, for example, research, those are things that while they keep you busy, they can be put off. Research, for instance, rarely has deadlines attached to it. Whereas when it comes to students, there's always a time consideration, a homework deadline, a test coming up, things like that. And that's why if a student approaches me, to the extent possible, their concern jumps to the front of the line. It's something that should we take advantage of. I want to see if I can get this right from a LaTeX point of view. Okay. Oh. Shoot. I was hoping that... Dang. I don't have a LaTeX command right. Something that causes text to be crossed out, just like the strike option in Word, but whatever. Point is, no more. Okay. Second thing, it's also tempting, especially after as many years as I've been here, if I could add up all the time spent, of a cumulative time spent in class waiting for students to put out any kind of answer to a question, when often they probably have a reasonable answer to put out, and wrong answers are definitely okay. The point is, to try something. Yes, thank you for closing the door down there. Okay. If I could add up all that time and find a way to bill you guys for it, I would. Because I am going to be putting out more questions for you all today, and I'd like to stick with. I don't like to just cold call on people because I know that can create a certain amount of stress. But if I have to, I will. And to make sure that it was random, what I thought about doing was writing everyone's name on a slip of paper and then and pull it out of a hat or something. But there's one logistical problem with that, and that is my handwriting is awful. This is an actual picture of the attendance sheet for today. Good luck trying to pick out your own name on that. Yeah. So some are easier to pick out than others, but if I look at this weeks later, it's like, what name is that? So, yeah. And to think that some of you wanted me to write on a board more. That's really funny. But I don't need to do anything like that because I have MATLAB. And what MATLAB does, and you've done this in homework 1, is generate random numbers. I even wrote a script. Here are all your names, legible, including people at the coast. And what this script does is it generates a random number from 1 to however many students are on the list, which is 21. And then it'll print out that name that it picks. So this is just a test run. Don't worry. Yeah. So and then if I just keep going, it'll just pick whoever. Now these are pseudo-random numbers, but that doesn't mean that someone see it picked on you twice and 3 times. So it's a good thing that was a test run. Okay, I swear to God, I did not do this. Okay. Yeah. Okay. But now you can see that, okay, like it picked on Carade, he's here, okay, twice in a row. So I will use this if I have to, no matter how many times it picks on Carly. So, okay. Okay. All right, I may overrule its judgment, like if it picks on someone twice in a row, I'd be like, no. Okay, but again, the point is, these are measures I'm prepared to go to. Okay, next item. This is something I want to try to add to the beginning of every class because it's easy to see whatever topic we're covering today, like in a vacuum, and it's important to be able to connect that to not lose touch with the big picture, or even what we've been covering lately, or we're going to cover in the near future. Not to mention the big picture of what's happening during the entire semester, or a longer stretch than just a few days. So I want to include in this reminders of what is the big picture, what is the smaller picture. Okay, have another name to write illegibly over here. Okay. Yeah. Yeah. But yeah, see, if you look at the code for my pick on someone script, I did not say pick this name or any other name more often than others. It's Randi. It's its fault. So keep that in mind. Okay. So just a reminder of a point of this chapter is approximating functions by polynomials. Well, let's start. Again, not picking on anyone, but just putting it out for all of you. Why polynomials? Yeah, easier to work with. Why are they easy to work with? I get the answer a lot in the quiz, but why? What is it about them? I'm sorry. From a computer point of view, what's does that? Yeah, the basic arithmetic operations. Okay. Okay. So, and that's the point of the chapter. Where we've just been is efficiently generating and evaluating interpolating polynomials. We've seen 2 approaches to doing that. First, Lagrange, and then an improvement on that, Newton. So that's okay. Now I'll point, and when I make these points, I'll refer to what's in corresponding part in the textbook. So this is all about chapter 6. The thing is, I'm actually considering taking chapter 3 in the textbook, which doesn't get covered till next semester, and splitting it into 2 chapters, 3 and 4. But then I realized it would throw all of you off. And you'd be doing the wrong thing for homework, so I'm going to have to wait. Lagrange, that was in section 6.2. Newton form is in 6.3. So like what I was talking about last time, using a divided difference table to generate it, and then nested multiplication to convert to power form, so that would be easier to evaluate. Okay, and then, so where we are, this is for today, is how accurate, once you have an interpolating polynomial, polynomial, once we have it. because I've already shown an example where it may turn out to not be very accurate at all, even if you're matching your function at many points. Okay, and then so where we're going with this is so the point of all this is how to interpolate wisely, how to choose. No, hello, I want to go into math mode, you dang thing. Okay. So how to choose the interpolation points. It's convenient to choose equally spaced. You see that in a lot of examples, but it's not always a good idea. Also, what's coming like next week is how to take derivative information into account if you have it. Okay, and where this is going is really so. This is so that last point is in section. Dang it. Okay, and this is. Again, this is how to interpolate wisely, how to choose the points. That's about Chebyshev polynomials, which I'll talk about today. And then question of how accurate, that's the main focus of this section, 6.4 for today. And then where this is going, as we get into the next chapter, the last chapter that will be covered this semester, is using the interpolating polynomial to approximate derivatives, integrals. And then, and where this goes next semester is it'll help with solving differential equations. Polynomial interpolation for certain methods, also Taylor series play a role in that. Okay, so the focus today is if we're approximating a function by a polynomial, how accurate is it? But one thing I thought of just now as I was typing these points out is okay, a contrast between Newton form versus power form. Okay. So as an example, Newton form would be, I'll do a quadratic example. Whoops, I don't want it here. Okay. So we have some coefficient, constant term, plus a linear term, plus a quadratic term. We saw this last time. Whereas power form, same polynomial, and this is what we got to last time. Okay, and get rid of these extraneous spaces. Okay. All right. So what happens is we can fill in our divided difference table, and we get the first form, and then we go through a hassle of decimal multiplication, or it'd be multiplying out if you did this on paper to get the power form. So why go to the trouble of power form? If you just look at what's involved with evaluating these. So again, keep in mind it's a computer that's doing all the work here. So what's desirable about power form instead of instead of leaving it in Newton form like this? What's the gain? Especially if you're going to evaluate one of these at like a zillion points. So why would the second form? What's preferable? What? Yes, less computation. What are we saving? Yeah. So fewer arithmetic operations. No subtractions. Okay, good. So, and because of the amount of computation needed to get this into power form, really, it's very little. We're talking for a degree n polynomial, it's on the order of, let's see, well, it's n order n squared operations, but n is typically small. We don't even like to do high degree polynomial interpolation necessarily. So let me fix my spelling error here. Okay. All right. So as far as attendance goes, let's see. I assume, Rachel, I assume you're the only one down there today?
Yes, sir.
Okay. Oh, by the way, and I'll send an email about this. What I'm thinking of doing is next Thursday, so November 2nd, that because I actually have to head down to New Orleans at night to that night to fly out the next day. That I would actually teach this class from the coast. So then that way I can take some time to help with assignments or whatever, like hold some office hours. But I'd like some assurance that it would be more than one person showing up. So, so I'll send an email reminding about that, but it's something I'd like to do. And then maybe even on other occasions as the semester winds down. Okay, so, all right. Sorry I haven't actually done that up to this point. Something that was always intended. Okay. Now, before continuing, does anyone have any homework-related questions? I know at least some of you are getting into Chapter 6. Well, ideally, all of you should be getting into Chapter 6 to some extent.
For 6.14,
right.
is for xi, are we still only supposed to be dealing with xi where I is equal to 0 to 1?
Oh, no. Okay, well, wait. You mean for the quadratic case?
Yes.
No, because for polynomial degree n, you're fitting at n plus 1 points. So you're going to add in, you're going to have, so to go for a new coefficient, a2, you're going to have a new point, x2. So you're fitting at 3 points, and then also, therefore, you're going to have a system of 3 equations. Okay, actually, let me make a note of that here. Okay. All right, so quadratic case, fitting at x0, x1, x2. System of 3 equations, 3 unknowns. So I mentioned the unknowns, but I didn't cover the rest of it. General case, degree n, n plus 1 equations, Pn of xi is equal to yi. For I equals 0 to n, and then n plus 1 unknowns, a0, a1, an. Okay. Any other? Chapter 6? All right. Okay. Since I ran out of time last time, there's one last point I wanted to make on section 6.3 and the explorations therein. Converting algorithms in the text to MATLAB code. So watch your indexing. So to give an example, one of the algorithms that needs to be implemented. Whoops. This one for divided difference table. So if you look at the indices, for instance, I equals 0 to n, and you're setting some variables equal to your f values. So algorithms are, as written in textbooks, for instance, are often using zero-based indexing. And programming languages don't agree on indexing. MATLAB uses one-based indexing. One is the first element. Whereas what language is not like that you've likely all been exposed to? C++ uses what? Zero-based indexing. And actually, from a hardware point of view, that really makes more sense. It drives me nuts that MATLAB doesn't do that, but Cleves will be done on that one, as in Cleve Moeller, the creator of MATLAB. Okay, so what you have to be prepared to do is often have to shift indices from what's written in the algorithm. So for example, like in this case, I'd have like maybe I going from 1 to n plus 1. So you're still going to have the same number of iterations, they're just going to be numbered differently. So this is something you have to be careful about. And what we have here is here I have di0, dij, djj. So there's two indices. So to translate this as directly as possible into MATLAB, that means you want to have D be a matrix. And I is always greater than or equal to j. So what you'd be doing is filling in like the lower triangle of the matrix, like from a diagonal entries on down. So D you have a matrix, but C it only has one index. That's a vector. So what I would suggest is so for exploration 6.3.6, in which you're implementing algorithm 6.3.4, test on example 6.3.5, because what you're given there is some sample data, and I fill in the divided difference table, so then you can make sure that you got everything right. And if you got that one right, chances are your algorithm works in general. I found that you can never test code enough, but at least certainly a minimal amount of testing like this is necessary. Okay. And for the other explorations in this section, you're writing a program that uses Newton interpolation to generate the interpolating polynomial in power form. That, for this example, is also worked out in full. So again, you have something to test against. Okay. Okay. But yeah, this is the main thing. Your indexing, but it needs to be adjusted. Okay. And that reminds me, I'm still occasionally getting questions by email. So there's been a couple recent entries on the questions page for Chapter 6. So be sure to check those. Okay. Alrighty. Any other homework 3 questions? All right. Let's see what I can do in these last 48 minutes that we have here. Okay. Now, so in this section, so the funny thing is, in section 6.3, all of the explorations that I assigned involve MATLAB, and in 6.4, none of them do. That's what I like about this class. There's a variety of problems, and in this section, you're actually proving some things. So the point of today is to give you some breadcrumbs so that you don't get lost in the process of trying to prove these things. So, okay. So here I'll just make a number list. There are 5 explorations that I assigned in this section, 1 through 5. So I'll just talk about, try to say something about all of them. Okay. Now, here we have, let's make this a little bigger, the error formula for polynomial interpolation. And so the first exploration that I assigned is to actually prove this theorem. Now, if you were trying to prove this like from scratch, that would be a huge ordeal. That is not what I'm having you do. Really, what I'm having you do is piggyback off of another theorem, 633, which is so here you're just using the result. So you can accept theorem 633 without proof. There is an exploration for proving it, but I didn't assign it. So I'm going to put up that one. Okay. So we look at the Newton form. Actually, I'm going to go ahead and put up Newton form. Using the divided differences. Actually, better do this as an equation array. All right, so we have constant term, but now I'm going to be a little more specific than I was earlier about the coefficients that we have, because they're all divided differences. All right, and now just fill in like the last 2 terms. Okay, so f naught x1 okay. Okay, that's more like it. All right, someone tell me. Here's my coefficient. This is second to last term. But if you keep in mind what I have up here for my divided differences, and then the products of linear factors that follow, then tell me what I should put in next, or I'll call on somebody. So if I have something like this, but how does it start? How does it end? What? Yeah, that's where it ends. So someone tell me in full, like start us off. Yeah, x minus x. Okay, keep going. Okay. Whoops. Minus x2 dots. Okay, and then like you said, we end at x minus x m minus 2. Okay. And then the last term. So what goes in the last term? Continue it for me. Yeah, xn. All right, and then yeah, so x minus x1. all the way out to x minus x n minus 1. So we have n factors multiplied here, which is what we expect because the polynomial overall is of degree n. Okay, now, so now what I'm going to do is we go to one of the hints in the problem that, okay, I need to go back to a problem. Okay. Work with the Newton interpolating polynomial for these points, x0, x1, up to xn, so the same points as before, and then I throw in one more that I'm just calling x. Now you might think, oh, x is a variable, but the thing is, it's an arbitrary x. So it's still something that you're allowed to use as an interpolation point because we're just focusing on a particular x in the interval AB that contains all of these points. Okay. So if we look at, so the thing to keep in mind is, can anyone recall what is the advantage? Because you would have filled this in, some of you on the quiz. What is the advantage of Newton interpolation as opposed to Lagrange interpolation? Right. So if I want, so I have let p n plus 1 of x interpolate f at same points, x0, x1, x2, xn, and then xn plus 1, then if I were to write out the Newton form, dang it. For Pn plus 1, okay, then I'm going to have exactly these terms. Plus one more term. What's that one more term? Sorry, what? Yep. Yes, xn. So same factors as before, but then there's one more multiplied onto it, xn. Okay. Now, but so the thing is, notice this product here, x0, x minus x0, x minus x1, all the way up to x minus xn. Okay, there's a, all right. That's what you have here. This is the product of x minus x0, x minus x1 up to x minus xn. So that's one thing you have working for you. But then theorem 6.3.3 says that for any j, the theorem uses n, but I want to use any index j, we have a following. F, the difference of x naught, x1, x2, up to xj is equal to the jth derivative at some unknown point over j factorial. Okay, so this is something. So if you take a look at these three items, what this polynomial degree n plus 1 looks like, and then this result here that can apply for whatever value of j is convenient for you, and the then the error formula itself. This is what you're trying to get. Then the goal is to see, can you put the pieces together to actually establish this result? So, so the thing is, if I so for a proof, x is some. Think of x as arbitrary but fixed point in AB, and then p n plus 1 interpolates f at x0, x1 up to xn and x. So so think of xn plus 1 as just x. We're just calling it something different. And what does this mean? It means that p n plus 1, this is about what the interpolation means in the first place, agrees with f at these points. So what does that mean? That means that, or another way to think about it that might not be so obvious is, so at these points where we're interpolating, the points that I've listed, Pn plus 1 and f are, you can think of as being interchangeable. So that's something you can take advantage of to polish this off. So those are the breadcrumbs I'm throwing out. We'll see if you can pick them up to find your way home. Okay. So any questions about what was done here? Okay. Now, okay, number 2. So number 2, not proofy. We're actually applying this error formula to a specific case. I give you a function f of x. I give you some interpolation points, x0, x1, x2. And so n is equal to 2 in this case. And you fill in the particulars in this error formula, and you see what you get. You try to find an upper bound on the error. So what I'm going to do is we're going to step through a similar problem. Okay. All right, so let's suppose that, dang it, stop it. All right, so fx will go with, let's see. I'm going to go with sine x. And x0 is equal to, okay, x0 equals 0, x1 is equal to 1. So in other words, n equals 1. We're approximating sine x by a linear function that agrees with sine at the points 0 and 1. So what the theorem, well, okay, let me fill in a little bit more here. So P1 of x is the polynomial first degree that interpolates at 0 and 1. So by the theorem, what we get is the following. So sine x minus P1 of x is equal to the second derivative at some unknown point over 2 factorial because it's n plus 1. So, so if I actually, I'm going to try putting both of these on my screen at the same time, if I can. All right. Okay, so here you can see the error formula. So f is sine, n is equal to 1, so I have f minus p1 is equal to f double prime at an unknown point over n is equal to 1, so 2 factorial. And then what I'm going to have is, oh, now I'm having trouble seeing what I'm doing when I type. Dang thing. Okay, just need to make this, all right, that should work. Times x minus x naught times x minus x1. So now what I need to do is go ahead and fill in the particulars here to try to get an upper bound for the error. So, second derivative of sine, what? Minus sine. Remember, my hearing is awful. So minus sine at some unknown point, squiggly, over 2. Okay. And then x naught is equal to 0, and then x1 is equal to 1. So now we have that. But now I need to establish where are x and squiggly. So squiggly is in an interval, lies in an interval containing all these points, 0 and 1. So that is in 0, 1. And what I'm interested in, I need to specify x. I want to know if this is interpolation. We're interpolating at 0 and 1, so x is also limited to 0 and 1. And what we need to do is get the sharpest upper bound possible. Because the thing is, I could be kind of half-assed about this to come up with an upper bound, but I want to get as close as I can to be as realistic as possible. Okay, now, I'll just be upfront and say that this is a trick question, because I know what you're likely to say. This sine squiggly, how large can it possibly get? Yeah. Okay, so yes, it is between minus 1 and 1. But tell me how we can narrow it down further.
You can assume the max, can't you?
What?
Can you assume the max? Like, say, assume that it's sine squiggly is equal to 1.
In this case, yes. So I can say that. Okay. Ah, dang it. Go, stop that. Guys think can be so uncooperative sometimes. Okay, so for squiggly, or C, 0, 1, we have sine is actually less than or equal to sine of 1. Who can tell me why we can say that? You think Cal 1. When you're finding maxes and mins of functions, what are you supposed to think about? Where are you supposed to look? What?
That makes sense. So, just the absolute value of sine, since it's always going to be positive, it's always going to be some decimal because of being sine.
Okay, I'm not sure if I'm following.
Sine can only be like you're only taking the values from 0 up.
Right.
Since
The sine will eventually, so from 0 onward, at least up to a point, sine starts out being positive. When does it go negative? I'm making you remember your trig now. Like, what's sine of pi over 2? What? Yeah. And what? And sine of pi? Yeah. What's sine of pi? Yeah. So it starts out positive, it stays positive until you get to pi. That's 3.14. We're only going up to 1. So on this interval, sine is always positive. Now, okay. Again, dig up your Cal 1. You are asked to find the maximum of or minimum of a function on an interval, which is exactly what we're dealing with here. I've specified an interval. How do you do that? Yep. Yes, and that gives you what are called what? Critical points. And okay, so you can check those. And what else are you supposed to check? Endpoints. Yes. Ding, ding, ding. So what happens? Okay, take a derivative of sine. It's cosine. But where's cosine equals 0? At pi over 2. And odd multiples of pi over 2. None of which are in this interval. So critical points would give you nothing of use. So what do? You check the endpoints. What are the endpoints? 0 and 1. And sine of 0 is 0. Sine of 1 is something positive. So that's why. So in fact, another way you can look at it is on this interval, sine is increasing. So you just plug in the right endpoint. Bam, you're done. So if you know the function is always increasing or always decreasing on a certain interval, then you just go ahead and plug in the appropriate endpoint, and that's your max or min. Now here you really want to look at both max and min if you take the largest and absolute value, and so that's what we have here. So sine of 1 is as large as that can get an absolute value. Okay. Now, so we've covered this part of the error. So now, someone tell me how to proceed with the rest of this. X times x minus 1. Okay, so for x times x minus 1, so we want so x is between 0 and 1 again. So using what we're just discussing, what's your next move? It was just talked about in regard to sine. We do the same thing here. Kristen, you're the one who said it. Yes, take a derivative. Well, what should we do with this before we take a derivative? Yeah, multiply it out. Do it for me. X squared minus x. All right. So, okay. And the derivative is what? 2x minus 1. All right, so critical point is what? 1/2. Okay, what happens at the endpoints for this function? Wait, what? And it's easy to plug in the endpoints. What do you end up with? Oh, the endpoints are 0 and 1. No, the endpoints are, well, yeah, but the thing is, if you plug in x equals 0 or x equals 1, you get 0. Because this is that's a factorization. So this is a polynomial of roots at 0 and 1. So you're not going to get anything useful out of the endpoints. It's just your critical point. Okay, so now we plug in the critical point. So what happens when we plug in the critical point? What do we get? Yeah. So max in absolute value is 1/4. Okay. 1/4. Okay, so now we can put everything together. So, so the error, absolute value of sine x minus p1 of x is less than or equal to, so we have sine of 1 over 2, and then we have times 1/4. So we include that also. So sine of 1 over 8. So let's go ahead and evaluate that. All right, so 0.1052. Okay, well, I should say approximately because we're only 4 decimal places. But so so the error cannot be any larger than that, and generally it's going to be much smaller. So at x equals 0 and x equals 1, the error is going to be 0 because this polynomial agrees with sine at those points. In between, this is the worst it can get, and actually it's not going to get that bad because. Yeah, this maximum happens at 1/4, but here we're taking the value of sine at the 1. Now, c is an unknown point. It can depend on x, but if you were to plot, well, actually, let's take a look in MATLAB. So, vector of x values, y values, polyfit, x, y, degree 1. So this is my polynomial. Y is equal to 0.8415 times x, and then 0 is a constant term, which makes sense because sine of 0 is 0. So now what I'm going to do is I'm going to plot x and then polyval px. I only need 2 points to plot a line. Okay, so there's my linear function. And then I'm going to make a vector of a lot of x's from 0 to 1. And then I'll plot x and sine of those in red. Okay, so the red is the sine x and blue is my linear function. And if you look at the maximum difference, it seems to happen right around here. And it's less than 0.1. So this is just an upper bound. It's a pretty conservative upper bound, but it's sharp as we can reasonably expect to get. So what you're doing in exploration 642 is this exact same process, but now there are 3 points to deal with. So when you have that product, x minus x naught, x minus x1, x minus x2, that's a cubic. You take the derivative to get the critical points. That's a quadratic, but at least you can get the roots. Well, you can always get the roots because you have MATLAB. The function is e to the x, so as far as finding a maximum derivative, that'll be easy to handle. Okay. So any questions about this process of finding the maximum, finding the upper bound on the error? So you're bounding this part based on what derivative you get, and then separately you're bounding this part. And the values of c and x you consider are from the same interval. So whatever interval contains the interpolation points that you're given. So in this case, 0 to 1. And in the problem, it's also 0 to 1. Okay. But so one of the points of today is to remind you of how unforgiving math is when it comes to lower level stuff. That you have to dust off your knowledge of Cal 1 to do this kind of problem. In fact, for another problem in this section I'll get to in a moment, you actually have to dust off your discrete. Or any other proof-intensive class that you've had. But first, all right, 643, using 3 different equations that are given to prove another one. Okay, and all of that's on this page here. That we have the Chebyshev polynomials are defined in a very unpolynomial-like way in terms of cosine and inverse cosine. And they satisfy this 3-term recurrence relation. So for k greater than or equal to 1, each Chebyshev polynomial depends on the previous 2. And the point of this problem 643 is to prove that this relationship using these trig identities right here. So, so the idea is, so the breadcrumb that I'll give you for this is, okay. Proving 6.16. So you want to apply the given trig identity 6.14, 6.15 to the definition of Chebyshev polynomials. So in particular, let this expression that's in 6.14, cosine A plus B, you want to fit that to t k plus 1 of x. So the Chebyshev polynomial of degree k plus 1, and then similarly, cosine A minus B should be associated with tk minus 1 of x. So if you were to go to the definition, which I'll put up next to it, this definition right here of your Chebyshev polynomials, in terms of cosine inverse cosine, but for degree k plus 1 rather than degree k, then the question you need to answer before going any further is, what are A and B? So this is all pattern matching, one of the most essential skills a mathematician can have. So you write out what tk plus 1 is in terms of the definition, also tk minus 1, and you set aside what's identical and focus on what's different, then figure out what A and B are. Then what you can do is substitute A and B into throughout these formulas here. And then see what you can do with these 2 equations. You have to use these 2 equations together to wind up with this one. Now, there are 2 things to keep in mind. How inverse functions relate to one another. So, first of all, for any function f that has an inverse, f of f inverse of x simplifies to just x. Also, don't bother trying to simplify sine A and sine B. I guess you can once you have A and B, of course you can plug them in there, but don't bother. Point is to get rid of them, because sine A and sine B do not play any role in the final equation you're supposed to get. So don't try any actual manipulations of those equations. Just get them to cancel out, that kind of thing. Okay. All right, so don't want to be wasting any time on that. Okay. Okay, 2 problems left in this section. I think I can finish all this in time. 644. Using that equation you're supposed to prove, using, where'd it go? Using this recurrence relation, defining each polynomial in terms of a previous 2. You're supposed to show, prove by induction, that the leading coefficient is a power of 2. So specifically, the leading coefficient of tk is equal to 2 to the k minus 1 for all polynomials except for degree 0. Now, who can tell me what is involved in proof by induction? What class did you see that in? Discrete, yes. Well, I guess some of you are taking it now, aren't you? So, but for those of you who might have taken it a while ago, so what is involved in a proof by induction? There are 2 main ingredients. What's the first thing you do in a proof by induction? Base case. Prove a base case, and in this problem, that would be k equal 1, because you're trying to prove something is true for all k greater than or equal to 1. So k equals 1 would be the base case. So in other words, the leading coefficient of t1 should be 2 to the 0. So you can just go ahead and check that directly, because it actually says what t1 of x is. Okay. Dang it. Stop that. Then what? So really the key step in a proof by induction is what? Yeah, so assume it's true for k, prove true for k plus 1. In other words, you're trying to show all the dominoes fall. Base case tells you the first domino falls. This proves that if any domino falls, the next one will fall. Therefore, all the dominoes will fall. Okay, so using your knowledge of this, using assumption of this, that the next one's going to work. Using 6.16. So for that, what is the leading coefficient of a product of 2 polynomials? So in other words, if you already know the leading coefficient of 2 polynomials, you go ahead and multiply those polynomials. What's the new leading coefficient going to be? Think that through. If you're not sure, like try a simple example. Just make one up, and you get the idea. So that's what will play a role in terms of seeing that the leading coefficient of tk is 2 to the k minus 1, that the leading coefficient of tk plus 1 is 2 to the k. What about a sum of polynomials? What happens to the leading coefficient in that case? So how the leading coefficient changes as you perform operations on polynomials, adding, multiplying, what does that do to the leading coefficient? And you'll see how that one works out. So anything I'm having you prove, not meant to be terribly involved. It may not be easy to come up with an overall path, but it's not meant to be a long one. Okay. Not looking to have to kill a bunch of trees just to write it up. Okay. Questions on this one? Quite the tour of a math curriculum we've had here. And not to mention not just discrete or Cal 1, but also including trig. And that also plays a role in this last problem. So finding the roots of tk of x, show they are real, distinct, lie in the interval -1 to 1. Okay. Now it says use the roots of cosine. So use So the thing is, use the definition of tk of x is cosine of k inverse cosine of x. So the thing is, since for any x, Chebyshev polynomial is a cosine of something. So what you're going to do is you're going to set this. You're going to set this equal to 0. So tell me, give me a description of all the roots of cosine. Actually, I blurted it out earlier, but yeah, and let's come up with an equation. I'll call it theta is equal to, oh, okay, don't want that. Okay, theta is equal to, okay, you said odd multiples of pi over 2. What's a convenient way to express odd numbers, like a formula? What? Yeah, 2n plus 1. So I'll use like a typical index, like a 2j plus 1 times pi over 2. So that would be where j is an integer. And we'll let j be 0, 1, 2, and so forth. Really, it's all integers, but I'll just, for convenience, start at 0. Because you also have periodicity to think about. Okay, so what that means is whatever is inside the cosine, k inverse cosine of x, that has to fit this form, odd multiple of pi over 2. So the idea is you can use that relationship to okay, so, whoops. So you equate to what we're taking cosine of to solve for x, because the Chebyshev polynomial is a function of x. So ultimately your expression should be x is equal to something, and because it's of degree k, you need k distinct values. Okay, so one thing to keep in mind is to show that they're distinct. Cosine of theta is a one-to-one function on the interval 0 to pi. What does it mean for a function to be one-to-one? No? That's actually what it means to be a function. You flip it, and yeah, so every y there's only one x. Okay, now, so in other words, it also means that it has an inverse. So, and now one thing to keep in mind, show the real distinct and lie in. Notice I put the open interval, -1 to 1. In other words, I'm intentionally excluding the values 1 and -1 themselves. And what you'll find when you get your formula, because of this odd multiple of pi over 2 thing, is that no matter how large the degree is, all the roots will be concentrated in -1 to 1, and they'll start filling up that interval, but it still won't quite reach -1 and 1. So this is something that can help. So in other words, your roots are going to end up being cosine of something. So if you can show that all the angles are, okay, so show that the roots, dang it. Show that the roots are cosines of, dang it, cosines of distinct angles in the interval 0 to pi. All right. So if you can do that, then that would show that because if the angles are distinct, cosine is 1 to 1, therefore the cosines of those angles are distinct. Therefore the roots are distinct. Okay. Now, this might not make much sense right now, but what I'm hoping is that once you solve this equation to get the actual x values, to get an actual formula, then you'll see what I mean about showing that they're distinct. And as far as like the real part of showing it that they're real, a polynomial degree k can have at most k roots. So if you come up with k values that happen to be real numbers, well, that's all the roots. So there's nothing elaborate to do there, just to show that all the roots are real. Okay, so any questions about any of the problems in this section? Okay, so hopefully there are enough breadcrumbs to get you through those, and I'm just going to keep going into the next section, 6.5, on Tuesday. So, and remember, there's one of the Canvas quizzes. I'm putting them out now and then, but one of them is due tomorrow. So most of you have gotten that in, but not everybody. If you handed it in but didn't get full points, you can go back for more. These quizzes do add up to a lot. So, okay. Scram.